Hi everyone, Nicole Grunucci here. In this video, what I'm going to do is talk about 1D motion. I'm going to basically introduce your first lesson in physics, which happens to be one of the most important. Not so much that it's, make or break in terms of the course, but it's the foundation of motion. So we're going to talk a lot about motion, and since a lot of things do move, as you might expect, it's good to know how to model it, how to recognize it, and of course, we're going to look at graphical and computational models when it comes to modeling motion. So we're actually going to start very basic here and talk about 1D motion, meaning we're constricted to one line. Motion can be 2D, which is as you see in that picture up there, as we look at here. So I didn't choose this picture because it models 1D motion, more that I chose it because it does model motion. This is more of a projectile motion kind of question. This looks like a ton of fun. I want to be there right now. Go skiing. I haven't done that in a little while. But anyway, the point is 1D motion is just a straight line. So whether I go like this or up and down, but I'm not breaking this constraint here. I will do 2D motion, which is this, projectiles. That's, a couple lectures as we get through this course. But like I said, we're just going to kind of stick to that. And I'm actually going to stick to one type of motion right now, which is constant motion. Excuse me. So obviously what that means is objects that maintain their motion. So we're not going to make them increase or decrease, start or stop, or do any sort of acceleration, which will be the next lesson as we go through. So like I said, there's different ways to model things. You're going to attach to some of these models better than others in terms of how to understand things. So as always, I like to give you a bunch of things to use to help you understand these concepts. So graphical models, these are called dot diagram models, whichever one you like, really. So it's all about constant motion. So we'll talk about and interpret position, displacement, and distance, average speed, and average velocity, which is different than constant speed and constant velocity. Then we're going to model constant motion on graphs. Both on a distance versus time and a velocity versus time. Fun fact, these are totally different ways to analyze the same thing, which makes it both confusing and challenging. So just heads up, this is challenging here, not because it's conceptual, it's not because it's like out of your reach in terms of hard. You're going to understand them separately. It's just, I find that when you do them, they can get complicated because they look the same and you might interpret one as another and all that fun stuff. So you'll understand what I'm talking about when we get to that point. Okay, let's get into this. So we're going to start off with components of length, because before we talk about something that's moving, we need to measure how far it's gone. So there's two types of ways we can measure length. We can measure the length as a distance, or measure length as displacement. Now, I'll just tell you, we're not going to calculate displacement or length at this point in the course. I could spend a lot of time on that. I'm not going to. I do want you to recognize the difference between the two. Distance is how far you go. So, what you see here is for example, a hike on Sleeping Giant or, or a trail, right? So distance is how far you've gone. So if this was broken up into different legs, like 1, 2, 3, and 4, you would add all those pieces together to get your total distance. Displacement, however, is different. Displacement is how far you are from where you started. So if you think about displacing your keys, usually imagine you keep your keys in the same spot. For example, right by your door every day. Maybe the next day you come back and you notice your keys aren't there. They're displaced, right? Where are they? They're on the refrigerator, or I don't know, something weird like that. Can't put them on the refrigerator. Maybe they're on the coffee table. How about that? So then their keys are not where they're supposed to be. They're displaced a certain amount. So that's what displacement is. Another key feature about the difference, besides their actual physical differences, is what they are. Distance is what we call a scalar, so it's a measurement without a directional feature. Notice that this purple dotted line has no arrow with it. The direction doesn't matter. But with displacement, it does matter. I did not only displaced it, but I am basically southeast of where I started. Now, we are not going to use methods like southeast. We're going to say we are 100 feet at 32 degrees below the horizontal. So we're going to be very specific about our displacement. So just know that in advance. But we're going to use displacement in physics because not only does it tell us where it's gone, but it tells us by how much. So it's a much better type of measurement that we're going to do. So like I said, you won't actually physically do these measurements. They'll be given to you. Now, there's times when things are more appropriate. Like, for example, if I want to know the height of the building of something that's dropped down, for example, even though the object has dropped down, so it would be, for example, like negative 100, the height of the building is 100. You know, we don't say it's negative 100, it's the height of it's 100. And I'll talk about more of that details later too as well. But distance and displacement. Now notice one key feature too before I move on is that the distance is either equal to or greater than the displacement. It can never be smaller than the displacement because displacement is always a straight line from point A to point B. So distance can always be bigger, but displacement cannot be bigger than distance here. So just a little quick fact for you. You might see that somewhere important. So because we're talking about motion and as a vector, meaning that it has direction, we need to have a convention to represent direction mathematically. And the most appropriate way is if you're going to the right, it's positive, and if you're going to the left, it's negative. If you're going up, it's positive, and going down, it's negative. We say convention means everybody does this, so everybody in this class and the world of physics sticks to this. Now, is there times when we can change convention? Absolutely, and I will do it for you, but I'll let you know when that happens. But in general, as you might imagine, if you're moving forward, it's positive, and backwards is negative. Now, it doesn't mean they're lesser on the number line. It just means the direction. So very careful with physics. People get this mixed up all the time. So why don't you take a quick little pause here. If we're starting at 0, okay, at location A, we're starting at location A. And then we have the two scenarios. We have B, where it's at 3, or C, which is at -4. Which one of these has the greater displacement? Is it 3 or -4? So take a second and think about this and submit your answer. Okay, so I hope you took a second to submit your answer. And I hope you realize that in terms of displacement, the greater displacement is from 0 to -4. Now, you might say, well, 4 is negative. Now, what you're looking at is not so much the negative. You're looking at the absolute value, right? The object went 3 meters in the first case. And in the second case, the object went 4 meters. The negative just means it went backwards. Forward and backwards has no bearing on the size of the displacement. I wanted to come back to this because I wanted to use my pen. Come on, pen. I'll give it a second, it's walking out. Oops. There we go. All right, let's use my pen now. All right, so if you look at, if I started here, for example, right? Why is it doing this? This is very unusual. Okay, one quick thing. Okay. Huh, interesting. This thing is really doing this. Okay. Wow. I'm sorry. My technology is wigging out for a second. Well, that seems a little better. Alright, I'll use my mouse then for a quick second. So from here to here, this is my displacement, right? And then from here to here. It's a little over, but that's okay. I kind of did that on purpose because I want to show you that this has a displacement of, well, it's actually delta x, the symbol delta x. But this one's slightly bigger, right? Delta x. This has a bigger displacement. It's just negative because it's backwards. So just careful with that. All right, so we have two different things that we can measure. We can measure this thing called average speed and average velocity. Again, Scalar means that there's no direction involved. It's just a measurement. So when you look in your car, hence the car figure right there, your car measures your speed. In other words, when I look at the speedometer over time, it doesn't tell me where I'm going, but it tells me how fast, right? That's a scalar. However, if you're like in an airplane, for example, you're going to go in a straight line, unless, I don't know, you're dodging a storm or some other thing. Usually airplanes travel with the same velocity. They travel with, 100 miles per hour northeast, for example. So that's a vector measurement. So vectors have magnitude and direction. Now the word magnitude, I don't want you to get confused about, because you will, because it shows up in homework all the time. Please give me the magnitude of this value. It just means the number. It's not a calculation you have to do. For example, you might get a velocity of 1,000 meters per second east. So the magnitude of that is 1,000. So you're just taking that number when it comes down to magnitude. So notice the difference between these calculations. Average speed is distance over time. Average velocity is displacement over time. These two measurements are different because one of them looks at how fast you went over time. One of them goes over how fast, in what direction you've moved over time. Dramatic. There we go. Now, keep in mind that when we do this, that we're finding our average velocity. So in other words, we're looking at how far we went over how long we went. So, how far you've gone over a period of time. So notice that the I means initial and F means final. And anytime we do delta here, that means we're taking a difference. So notice we took a difference between these two values. Typically we don't do this case. We just know the value that you went, and the initial conditions are usually 0. So we usually just totally ignore xi and xi and ti, and as this is 0. But graphically it might be different. Also, so this works for constant motion, for an object moving at a constant distance. If the object is not moving at a constant velocity, you can still find the average velocity by taking the two velocities and dividing them by 2. Please note the big difference though. This is assuming that the velocities are different. This is assuming the velocity is the same. Now the reason why is because if you're going the same interval over time, then you can do this calculation. But this is not, if this is the constant velocity, this will be silly because then it's VI plus VI because it's the same velocity, which gives you 2VI. 2VI over 2 is just VI. So just notice the difference between these two. But I wanted to show you an average velocity visual of a changing velocity to show you that you never are getting the initial or the final. You're just getting, I hate to use the word average, but you're getting the middle point velocity here when you calculate average velocity. Just like displacement, you have signs of velocity for the same thing. If your velocity is positive, you're going up or to the right. If your velocity is negative, you're going to the left or down. How do you know you're going left or down? You have to use the context of the question. The question will be pretty obvious in terms of, is it going to be restricted to a line like this, or is it going to be restricted to a line like this? It does give you information about that, so you can decide which it is, left or down. It's not going to be some mystery. Another point I'd like to make about average velocity is the following. So just like I kind of talked about, so say I want a total displacement of 5 miles, and I did that in a time of 0.2 hours. So my average velocity is 25 miles per hour. But if you look at this animation, right, I'm going to say a really silly thing, but just go with it. Did I go 25 miles the whole time? I hope you realize the answer is no, because I actually hit 2 stop signs where I'm clearly not going 25 miles per hour. So it gives you an idea of my motion, not a very specific type of motion. So just know that. Your cars do this too. So I used to have a commute that was an hour and 10 minutes. So my average velocity was either 45 or 50 miles per hour, which I found was really interesting because I was clearly doing 80 miles per hour on the highway. Don't tell people that. So I was like, wow, I feel like my average velocity is very small comparatively, but it is because it's taking into account all the times I stopped. My average velocity now that I work closer to home is 25 miles per hour. And same thing, I definitely do not go 25 miles per hour in probably any setting, at least a little faster. Don't worry, I'm not a crazy driver. I'm pretty safe, but I definitely don't go 25 miles per hour at a 25 zone because everybody else is going faster. Let's just blame everybody else. Anyway, let's not go into my car antics. The point is, I was actually pretty surprised when my average velocity was way lower when in reality I'm going faster. So it just gives you an idea of your velocity. So instantaneous velocity, right, is the velocity going at that one moment. So when you look at your car speedometer, not the, I have a new car, it's not new anymore. So first car I bought since I graduated, so it's new, but it's not new anymore. It was cool because I was like, oh, look, it tells me my average velocity. It's one of the statistics you can get out of your car. But if you look at your speedometer at any one moment, that is your instantaneous velocity. So I always get mad when, of the 2 times in my lifetime I got pulled over by a cop, it was within 2 weeks of each other in the same spot. Don't worry, I learned my lesson after that. But, I'm driving the speed limit, and maybe a little faster. Cop catches me. I'm like, man, my average velocity is like 60 miles per hour. But you caught me that one time. I went very fast. Got the instantaneous velocity, right? But maybe the whole time I wasn't speeding. So, that's instantaneous velocity when that cop gets you, right? As they should, by the way. And I deserved it both times. It was going very fast. But it was like 5 a.m. Nobody was on the road, and that was fun. Oh, gosh. Got 2 tickets. Those are the only 2 tickets in my life I've ever gotten. So I guess that's pretty good, right? Haven't done it since. But anyway, I'll just tell you, not going to ever calculate this. I do want you to be aware of it. What we're doing is actually taking the slope at one instant. So notice the x over t is like a slope, and you're taking the limit of that and blah, blah, blah. So I'm not going to go into it because you're not going to do it. But if I wanted to find the velocity at one instant on a graph, I would just take that spot and find the slope of it at that one point. You're getting the tangent of that slope. That's the instantaneous slope. If you really want to know more about it, I'd love to show you because I do like this stuff, so I can give you more. But I'll tell you again that you're never going to calculate this in the class. Just be aware of its definition. Okay, so now what I'm going to do is just take a gear shift here. No pun intended. Like that one. That was a good one. See if you're paying attention. I make lots of bad jokes. I'm not sorry. Not sorry about bad jokes. Okay. So what I'm going to do now is solve a few examples showing you the difference between these calculations of displacement and, speed and velocity and how they apply. So let's take a look at this. We're going to do some foraging bees, and they move in straight lines away from their hive. Totally realistic, right? So suppose a bee, hopefully my thing's working a little better now. So suppose a bee starts from the hive and it flies 500 meters east in 30 minutes, 400 meters west in 30 minutes, and then 70 east in 80 minutes. What's the bee's average speed and average velocity? All right, so since we're going back and forth here, I'm going to draw the beehive in the middle. We're mostly going east though, so let's mostly in the middle. So here's our beehive. Everyone talking to you like you're in the classroom, but why not? Does anybody harvest bees? Not harvest bees, but harvest honey? And beekeepers here. I draw an adorable little bee. Oh, he's so cute. Look how cute he is. Oh, such a cute bee. Okay, gotta have a little fun here. I'd be losing my mind, so I hope you're coming with me on this. All right, so here's our little bee. He starts at the hive, and he goes 500 meters east. So 500 meters east. So first of all, I'm such a visual person. I could not solve this without looking at pictures. I'm going to tell you that right away. I think it's just much clearer when you have it as a visual. So I highly recommend drawing a picture. actually forces you to organize things, or diagram, whatever you want to call this, because it forces understanding. My mind goes way too quick. I make lots of little mistakes because I just jump to things instead of like taking my time. If you're like me, this is super helpful. Some of you can just do this in your heads and oh my gosh, awesome, do it, totally do it. But for me, I like to do this. So notice what I did. I'm dissecting my problem. So I see that I have this measurement, right? And I'm going to keep things together and organized. So I'm going to put the time on the bottom and the distance on the top. And then because I have colors, I'm going to go ahead and color coordinate these. So then it flies 400 meters west in 35 minutes, okay? So 400 meters, so it's a little less than 500, right? And because of that, I'm going to actually draw this a little lower. Now, obviously, this V is going to go in a straight line. I hope you know that, but because I want to just separate the motions just so I could see them better, I'm not going to stack them on top of each other. So this is 400 meters west. In fact, you could even do stuff like this. The arrows are super helpful, and this was 35 minutes. I'm going to go back to making an arrow on this east. And then 700 meters, that's a long way, from this spot. So again, I'm going from this spot, and it's 700, so I have to go 400 plus about 300, so about over here. 700 meters east, and then 80 minutes it took me to do this. Okie dokie, here are our ways. We gotta do speed and velocity. Speed is total distance over total time. And let's do that one first, because we got it going here. So speed will be my total distance. So my total distance is 500 meters plus 400 meters plus 700 meters. So notice I ignored the distance because distance doesn't include direction. I'm sorry, I ignored the direction of all these cases. And then the total time. We have 30 minutes plus 35 minutes plus 80 minutes. Now, unless the question says so, you don't need to convert this to minutes. I will anyway because I anticipate you're mastering physics wants everything in seconds and meters per second. So I'll do that as a last step, but more importantly, I hope you notice I've taken total distance and total time. I'll go ahead and calculate these. 1600. Now I'm going to do 35, 30, 80, and 45 minutes. So speed will be 1600 divided by 145. So this becomes 11.03 meters per minute. Actually, I'm not going to write it like that. So that's a correct answer because it doesn't specify otherwise, but as the physicist in me would do, let's get this into seconds. So this would be 0.184. This would be meters per second officially. Pause this for a quick second. Okay, so that is our speed. This is it in meters per second. So on average, my speed is 1.84 meters per 1 second. So it's moving pretty slow, if you think about it. These are slow. Silly thing. Like that. So that's our total distance and total time. That is our speed. Now what we're going to do is we're going to do our displacement. So our distance and our displacement. So velocity is displacement over time. Now the good news is the total time is the same, but our displacement's different, right? I'm going to show you first visually the displacement, and then I'm going to show you the calculation. So notice the B starts here, right? And it ends up, even though it went backwards a little bit, it ended up basically over here. So this spot right here. So my delta x visually looks like this. So it's got to be east, and it's going to be a little more than where I started, right? Hopefully that makes sense. I can draw my B again. QB time. Get a little smushed. He's not as cute as my original B. He got a little smushed. That's okay. So that's the displacement. So how do we calculate displacement? The best way to calculate displacement is the following. So for everything that is forward, we're going to make it positive. So since 500 was east, that's positive. I'm going to do this a silly way, but you can do it the other way. But I'm going to add, because I'm going to sum them, negative 400, right, because we went 400. And then we're going to go 700. So notice that I'm adding all of the vectors, and one of them is going the opposite way. And that's why I have it as this. Can you do 500 minus 400 plus 700? Yes, you can. But my physicist in me is keeping things consistent, so I'm adding all the vectors together. So what happens? 500 minus 400 plus 700 gives me 800 meters. My velocity is different, right? 800 meters divided by, what did I get for seconds? I got 145 minutes. Like that. So I'm going to take those two numbers and I'm going to divide them. 800 divided by 145. And then I get hold on 1 second, sweetie, 51 meters per minute. I'm recording the lesson now, okay? So now that's meters per minute, so I'm going to convert that into seconds. So we know that in 1 minute there are 60 seconds like that. So I'm going to take that and divide it by 60. And then I get a really interesting number, right? I get 0.09, and I'll round 2 meters per second. There we go. So that's my velocity. So my speed, I'm going to put the two numbers together so I could tell you what it means. So my speed was 0.183 meters per second. My velocity was 0.092 meters per second. So it's really interesting because we're actually looking at the same motion, right? We're taking a B and we're watching it go back and forth like that. But we're looking at the motion in two different perspectives. Oops, good thing I can go back. The first perspective of motion is the total, basically, how fast it was going overall without thinking about the direction. So it was going about 1.83 meters per second. I'm just making sure that it matched up here. It does. Well, I put 8.4. That's okay. It's slightly different. Hold on 1 second. Okay, good. Sorry. Okay, so, but notice that this number is smaller, right? Remember, velocity has direction with it. And the reason why this is smaller is because your displacement was smaller. Some of the time was going backwards, and the other time was going forwards. So, if you notice, if your velocity is positive, you spent most of your time moving forward. If your velocity is negative, you spent more time moving backwards. And a really interesting thing is if your velocity is close to 0, you spent your time close to your starting point. In other words, you're not forward, not backwards, you're around where you started. In fact, if you get 0, you're back where you started because your velocity includes that directional feature. So your velocity has a signing component that's very important. Now, I didn't write the sign in here, but I'm going to go ahead and do it right now. So we spend most of our time moving forward, where this one has no sign. Okay, so just be careful with that. So I hope that makes sense. We spent most of our time moving east because we had 500 and 700. We had a little time moving west, which is why our number is a little smaller. And that's 2 ways to interpret this. So this gives you the directional feature. This just gives you generally how fast the bee went. So you have 2 ways to model the motion, right? Now, it depends on your situation, which is better. For things like moving in your car, your speed's better because, your car goes in all different directions. We don't really need to really look at where we're going because it ultimately it changes. But this is good for like an airplane or something that needs a direction because we need to know not only where you're going, or how fast. So how we model motion depends on the scenario. Okay. If you have questions on this, and I hopefully set this up right, ask them in the comments section on the side right here. So, I'll come back and try to answer them as we go through the week and address any of your questions you might have on this. Here is just another way we can see the question. So I'm going to tell you right now, while it's early in the course, that every question you see will be different. It's not because we're trying to make your life harder. It's because we need to be able to translate the understanding to different scenarios because it turns out that not every motion is going to be like a bee going back and forth. Motion is complicated. Motion can be a car that accelerates, slows down, and stops. It could be a projectile motion going up and over. It could be an object being dropped but then has a parachute. So motion doesn't have a one-size-fits-all application of it. So you're going to see that aspect of it in the homework. Now, my job as an instructor is try to give you all the techniques and tools to do multiple problems, regardless of the type of question that's asked. So just know that in advance, that not every question will match your homework question. I'll do my best to because I know there is some benefit in repetition and going over the same questions that I do. But you're going to see different reiterations of things, different ways to apply things, and that's on purpose. So, of course, I'm here to help you throughout this whole thing. With that big introduction, you're going to see that this question is different than what I just did, and I know that, and it's on purpose. So let's take a look at this. Michael Johnson's record 400 sprint. He ran the first 100 meters in 11.2 seconds. Then he reached the 200 mark after a total time of 2.13 seconds had elapsed. Then he reached the 300 mark after 31.76 seconds and finished in 43.81 seconds. During what 100-meter segment was his speed the highest? During this segment, what was his speed? Okay, so this one is, of course, a much more complicated motion we're looking at. We're looking at somebody sprinting 400 meters, right? So we're sprinting 400 meters. So 1, 2, 3, roughly, each like that. So again, I'm a visual person. I need to organize my information. Let's see. The first 100 meters, they did in 11.20 seconds. Okay? 200 meter. After he reached the 200 meter mark and had a total time of 21.32. Okay, so that's fun. So that actually means that instead of doing it like this, I'm going to do it like this because it's giving us total time, not segment time. Notice the difference, right? I'm here at 11.2 seconds. I'm here at 21.23 seconds total time. And when you reach this, he's at this point. And then finished here. Okay, so, and this of course would be 0 time, right? So they gave us total time, not segmented time, which is fun because I actually need to know the segmented time to figure out which time he was the quickest. So with that said, I'm going to find the segmented time by taking the number before and subtracting the number after. So 11.20 minus 0. This is the segmented time. Okay, and then I'm going to do 21.32 minus 11.2. This is 10.12 seconds. I hope you're okay that I'm not showing my subtraction. I'm doing this minus this. 31.76 minus 21.32. Seconds. And then 43.18 minus 31.76. Like that. Okay, so that's the time for the segments. If I want the speed of each of those segments, it's going to be 100 divided by the time. Because from here to here is 100. Oops, that's a 1, 2. See what I'm doing here. Oops. Got too comfortable. There we go. Okay, so then I'm going to go ahead and find out how fast they're going per segment. Okay, so now, oops. So we have, it says, during what 100 meter segment was his fastest? So now that I went through and calculated all those, we would find that the highest number is segment 2. So the answer is basically during the 200 meter part, they're going the fastest because it's the highest number. Okay, so I hope that you found that this was true because it had the highest number. It says during what segment was his highest speed? During this segment, what was his speed in meters per second? So this was the speed in meters per second. So there you have it right there. For funsies, I'm going to do the whole thing. So what's the average speed in general? So this would be total distance, which would be 400 meters. Oh, I know why my pen is not working because it's not charged. Okay. So I'll use my mouse really quick while it charges. 400 meters divided by the total time, right? Total distance divided by total time. So the average speed, sorry for the penmanship, I think you know what I'm doing here. As the average speed was 9.26 meters per second, like that. Okay, so there's another way you can use these equations. And notice I did speed and not displacement, although honestly displacement would be the same because they're moving forward the whole time, so the average displacement and the average speed in this case, the average velocity and the average speed in this case are the same, because we didn't go back and forth in that case, like that. This is a fun question. This requires a little more time and thought. In fact, I actually would like you to take a second and try this. I want you to know that this is a complicated question, that it's not straightforward on purpose. But I also want you to know that you can do this question, because I know a lot of people like, why did you do this to me? So I'm actually going to pause right here for a moment while you think about this question and attempt it. Now, despite the fact that you may not know the answer or feel like you're not confident in reaching an answer, you should reach an answer anyway. It's far more valuable for you to think through the entire question, even if you know it's wrong, than to give up because you don't know what the answer is. Now, the reason why I tell you this is from personal experience as a physics major. I'm sorry, I'm telling a story, but I'm going to go ahead and tell you a quick story. So when I first started physics, I used to always look for the solutions because, it makes a ton of sense, right? If I know how to do it, I'll know how to do the next question, right? The problem with that is you run into the two things. You run into two problems when you do that. One, you rely on solutions. So in other words, you need a solution to solve something. So that's not helpful in the long run because you're not learning how to solve problems. You rely on something else. So number one, to become better at problem solving, do not rely on other people. You have to be the problem solver. Second is that problem doesn't match anything else, which is back to my first point. But even more important, besides not matching, is the fact that you are losing out on thinking, which is what you need to develop over time. It takes a little while to do this, so don't get discouraged if you're having a hard time doing this because, again, personal experience, it takes a little while to learn how to think on your own and what to think about and how to think. Because I know a lot of times when you see me do these questions, you're going to say, wow, yeah, that makes total sense. And then when you do it yourself, you're going to find a total different experience because I'm not doing your thinking. You have to come up with those concepts, those ideas, and all that, thinking strategies on your own. So I'm sorry that this was long-winded, but I feel like I need to say it, especially since I have a little time to tell you this, but it's very valuable, especially now in the beginning, to learn and practice thinking on your own and coming up with an answer even if it's wrong, because it is a lot easier to change your process when you've already spent time doing it as opposed to not starting the process at all. And it takes hard work. I'm just going to tell you straight out, it takes hard work, but you can do it. You can. Just how much work do you want to put into it, but I highly recommend you do it. Okay, so that was enough talking about that. So like I said, I'm going to awkwardly pause for a minute because I do want you to come up with an answer for all three of those parts. This problem will probably take you 10 minutes to do. So, this would be a great point to stop the video and get a drink of water or whatever and take a quick break. In fact, I think I'm going to stop the video entirely and start the next video. Do I want to do that? No, I'm gonna pause. Okay, pausing. Okay, we have paused now. All right, so the Mamba question. I'm gonna do this a little faster than I've been doing it. I'm doing that on purpose. So I want to take a quick peek of where I am in my lecture slides. Actually, you know what? I think this is a really good place to, I'm going to stop my lecture after this and start a new lecture just so I can pace it a little better for you so you're not like drowning in, a single lecture. So I'm going to go ahead and do that. Okay, so I'm going to solve this for you. All right, so the Mamba, right? So the black mamba is the world's most poisonous snake with a maximum speed of 18 kilometers per hour. So automatic red flag here is this, of course. We need to convert that. That's fun. Suppose the mamba is waiting in a hideout to seek its prey before it begins to slither with that velocity. So notice it's positive, away. So this is moving forward. After 2.5 seconds, the mamba realizes that its prey can move faster than it can, and the snake turns around and slowly returns back to its hideout in 12 seconds. Calculate the average velocity during its return trip to the hideout, the average velocity for the complete trip, and the average speed for the complete trip. First step is to realize and diagram out what we have. So we have the black mamba, so we have a nice black snake. There he is there. Give him a red tongue. There he is. Beautiful. He sees, I don't know, what snakes eat? Mice? There he is, the little mouse. I don't know, it's a weird hair. Okay, so the black mamba, suppose, is waiting in the hideout. His hideout is here. He begins to slither towards it in 18 meters per second. After 2.5 seconds, he realizes it can move faster and then returns. So it doesn't tell us how far it's gone, right? So basically all we know is that it goes forward, and it says that it does this for 2.5 seconds. And then this thing is just way too fast, so that thing goes, and then it goes back to its hideout. Now, first of all, we don't know how long this time was. It just says it was, oh, it does. It slowly returns back to its hideout in 12 seconds. Oh, good. So we have that time. Good news. I don't have the redo button. No, I do. Good. So this takes 12 seconds. We know that this thing is moving at 18 kilometers per hour, which I have to convert. It's annoying. Okay. So why don't I go do that really quick? So 18 kilometers per hour. So in 1 kilometer, there's 1,000 newtons, 1,000, sorry, meters. And then in 1 hour, there's 3,600 seconds. Surprising number of 5 meters per second, like that. Is that right? I'm gonna double check that. I think that's right. That's right. I'm just a nice number. Okay, looking good. So this thing's moving at 5 meters per second forward at that time. So let's see. The average velocity during the return. So let's go ahead and look at that. So to find the average, part A, to find the average velocity during the return, I would need to have the displacement and the time. I don't have displacement. Notice that I don't have the return, I don't have the distance here. But what I do have, I have the time, because that's the 12 seconds. But what I can infer is that the time, the distance there should be equal to the distance back. Hopefully that makes sense. So what I'm going to do is find the distance using or the displacement of the trip out, because I have that information. In other words, I have that it's 5 meters per second, and then I have delta x is what I'm solving for, and my initial trip there is 2.5 seconds. So if I do the 2 times 2.5, it's 12.5. 12.5 meters per second. Okay, so, I'm sorry, not meters per second, meters, like that. There you go. Okay, so the displacement, or in other words, the distance the snake has traveled during that time, is going to be a total of 12.5 meters. And there you go. So now I can solve for the velocity. So the velocity of the return is the following. So it's just going to be the return, so from here to here. So it'll be negative 12.5 because I am going opposite, because the snake, our new starting point is where the snake is, right? The snake's starting here during the return. Yes, just go with it, okay? So the snake's starting here, and it's going left. So it's negative in this case, and the time is 12 seconds. I got a negative 1.04 meters per second, which hopefully makes sense because it took about 12 seconds to go about 12 meters. So it's about a meter per second like that. So that looks pretty good there. And then, let's see, negative because it's going left. Okay, great. Or back, or whatever you want to interpret that as. Part B. Part B is asking for the Mamba's average velocity during the entire trip. Well, the Mamba went forward and back, which means the displacement of the Mamba is actually 0, right? Because it returned back to where it started. So that makes that calculation easy. So 0 meters divided by the total time, which would be 2.5. I'm going to go through the calculation anyway. Plus 12 seconds, right? The 2 times. It's going to be 0 meters per second. So actually, you didn't have to do that. If you see how long it takes for a round trip, coming back to where you start, it's going to be 0. So that's the good news. But I went through the calculation anyway. The last one is the speed through the entire trip, right? So speed is distance over time. So now I need the distance over time. Now it goes 12 meters there, 12 meters back. That's the good news. And then I have to divide by the total time, 2.5 seconds there, plus 12 seconds back. So I believe that is 25, if my math is serving me correct. And then that's 14.5 if I add those two up. I'm just getting self-conscious, so yes, I'm just making sure everything's looking good so far. 25 divided by 14.5 gives me a speed of 1.72 meters per second. So once again, I'd like to just point out the different ways we can model the object. In one case, I have the speed, which is 1.72 meters per second, and the velocity is 0. Notice the different information we have here. Basically, with the velocity of 0, it means either the object didn't move or returned to where it moved. So this is basically saying that the object came back to start. So it does give us some indication about the direction, right? It went forward and backwards. That's what 0 means. Or it went up, down, up, down. It doesn't matter. It's all going to be back to start, so that's that. Now this tells you a little more information, right? This is more helpful because it tells you on average how fast it went. Almost 2 meters per second. So that's pretty fast as a snake if you think about it. I don't think I want to be near that snake going that fast like that. So yeah, so again, I'm going to put comments here, so if you have any comments about this question or questions, maybe myself or classmates, of course, I'm going to try to make it interactive in that sense to help you answer some of the questions for this question. And then I'm going to pause the video and start the next video session on looking at this all graphically.